Hello everyone, thank you for the invitation. The title, as we said, is a new approach for the fabrication of orthopedic implants, and it mainly concerns an FP7 project called the New Generation of Orthopedic Biomaterials. Some of the people working on it are Doctors Katarina Georgiatou, Miltos Vasiliadis from CETRI, Yan Huang and Krishna Burgapalli from Brunel University, as well as many others from CETRI. On the outline of this presentation, there shall be a few words on CETRI's profile, because Sakis discussed this morning. Then we shall move on to the state-of-the-art, the objectives and the innovation that lays on it, the chosen materials and methods, perhaps a few words on the participants and their roles, and some early results. CETRI is a privately funded research center in Cyprus, whose mission is to make a real impact to the society by addressing European and global market challenges and by providing state-of-the-art technological solutions. We currently have 6 FP7 projects and 10 Horizon projects funded. There are people with various disciplines working in CETRI, such as materials, energy, ICT, environment. We're very active in proposal development, so we can find funding opportunities for our partners, help them build up the consortium, write the proposal, submit it, and hopefully manage it. And we're also active in innovation management, which is all about creating value from novel ideas. On the new Biogen project, osteoarthritis is a very well-known disease. It's becoming even more evident in younger people, younger ages. However, the orthopedic implants, the currently available ones, do not fully address the patient needs. In fact, they're underperforming with respect to their biocompatibility, their strength, their wear and corrosion resistance, and their protection period. As a result, the patients requiring hip surgeries submit themselves to painful, expensive treatments that, on top of that, need to be repeated after several years. So they're not working. It's always about the materials and the methods and the production methods. Most of the hip and the knee implants, they are currently made of a titanium alloy known as grade 5, or its alternative, which has niobium, which was specifically manufactured to replace the first because of the cytotoxicity that thorium shows. However, both of them contain aluminum, which has been reported to be somewhat correlated to neurological diseases like Alzheimer's. And on top of that, they have substantially higher elastic modulus than that of the bones, resulting through the stress shielding effect. There was a discussion about that yesterday afternoon in that session. It mainly means that the body tends to remodel to the changes that we impose. So if we use an implant whose elastic modulus is higher than that of the bone, then this will take over all the strain, and then we will have bone atrophy. We don't want that. There are some raw materials that have shown some promising results in the lab, but as always, if you want to scale up to production, there are several changes that you have to do. So what we need is innovation in biomaterials production in terms of biocompatibility, mechanical and surface properties, and I may add that product life cycle is very important, because we don't want the patients to come back for treatment. So what we need is an innovative product produced with an innovative production process. We want a low modulus, which will be near to the bone, so approximately 50 gigapascals on top. It shouldn't be toxic, since it's an implant. It should have such a price that a company can take over its production. This relates to the discussion we had this morning on the innovation actions on FP7s and Horizon projects. It should have an enhanced wear resistance if it's going to be a knee or a hip implant. And it should last more than current solutions available in the market. The raw material that was chosen for the new Biogen project is a titanium alloy again. It contains niobium and tantalum. It's non-toxic as it contains fully biocompatible elements. It has the elastic modulus values that we need, so that's fine. Tantalum is immune to all acid environments, that would be our body. There are several positive things about this alloy, most important of which it decreases the modulus of elasticity of beta-cese titanium alloy without compromising their strength. That's fine, but it's a fine selection, but can we produce it? If we try with conventional methods, there can be some problems because this is a metal with various densities, relatively high melting points. It's very reactive with oxygen. So we don't want the risk of chemical inhomogeneity. We want to avoid this because this would mean dendritic structure, and that would mean affecting mechanical properties, and we don't want that because we want to sell it as a product. We could always remelt it several times, but that would mean very high energy costs. This is not a problem for powder metallurgy, as it can be treated with simple mixing of powders. So the decision was that niobium and tantalum will be mixed under argon atmosphere to avoid the oxidation of powders. And there will also be a study of grain sizes with respect to the porosity of the product, which is of interest to us because it affects tissue ingrowth. And you should be the experts on that, not me. And cold isostatic pressing provides high control to porosity, and we can also avoid energy costs. Are we done with our selection? No. So far we've managed to address the modulus that we wanted, the price that we wanted, because we've selected a good production process. Its biocompatibility is just fine, but will it work? Friction does occur between surfaces of moving implant parts and the bone surface in contact with the implants. If the implant that we chose or produce or put into the market has a low wear resistance, then the friction can lead to the release of metal shavings in the blood. That would mean a premature fracture of the implant and possibly allergic reactions, I would guess. So what we chose is a biocompatible wear-resistant zirconia coating, which will be employed on the implant surfaces where wear control is important. Some background on zirconia. Some of you may have heard of it as a fake diamond. It was used as such. They have been proposed for total hip arthroplasty because they are wear resistant. And they put a barrier to metal ion release, so that's good. However, they delaminate and brittle fracture might occur, so we have to be careful when processing zirconia. Especially with high temperatures and long processing time, which might affect the substrate. Another view on the literature, oxidized zirconium alloys have been shown to exhibit lower friction and superior wear properties. So that's perfect. They're very good for knee and for hip implants. And the wear rate of laser oxidized zirconium was found to be 2 orders of magnitude less than that of as deposited zirconium. In general, to sum up, we chose a material that's hypoallergic and biocompatible. But how are we going to deposit it on the titanium alloy? Well, it's a 2-step procedure. First, we're going to deposit zirconium on titanium alloy substrates in one process step under argon atmosphere, so no powder oxidation. And then we will oxidize its surface to develop the thin film that we want. We will do so by a new production process called laser engineered lens shaping, or else lens. This will be used to apply a high quality zirconia coating on the moving parts between the implant and the bone, the ones that have the biggest demand for wear resistance. So it should increase the wear and corrosion resistance, this new coating. On the side of this project, also fully automated machineries will be developed for the manufacturers. We'll see that in other slides. This is a schematic of the lens procedure or process. You might want pay particular attention to the powder delivery nozzles that you see on the left and on the right. There's 4 of them. And in the middle, there's a laser beam, the focused laser beam. The cladding material is in a powder form, and it's introduced on the surface where we want it with the help of a carrier gas. And the powder is trapped there, and as the laser passes, it quickly solidifies. So at the end, what you have is an addition of a new material where exactly you want it, safely. This is an interesting picture that I found on the web. It shows exactly how the orthopedic implants, a hip implant, looks like. So you have an acetabular component, a plastic liner, and a femoral head. And on the right, you can see a schematic of what this project will produce. It would be an acetabular cell design, titanium, then zirconium, then the oxidized zirconium, which is zirconia. These are the partners that are working on this project. NTUA, TICLENS will provide this technology, a hospital, Brunel University also, JDT for the machinery, Souzana Sofou. The American friends probably don't know this, but in European funding programs, you have to list your work packages briefly. So as a first stage, we'll generate all specification and requirements. We have to investigate the process parameters as we're introducing a new process together with a new material. CIRIC and GDT will be developing mixing and packaging equipment and some automated scale-up production machinery for their implants. Of course, we will develop and first research zirconia by modifying various parameters like oxygen flow, thickness of coating, and so on. And we should be able to test the implants for biocompatibility, wear, and corrosion resistance, and porosity, as we said earlier. Ideally, we should be able to compare it with commercial implants that we're going to do. And there are also dissemination actions and management actions. Some very brief look on the results. Structural characterization, tribological testing, and cytotoxic studies are the main parts. Here you can see a SEM picture showing very clearly the zirconia coating on zirconium. Just to mention that there have been tribological testing as well, according to an ASTM standard. Good wear rates were found, and also cytotoxic studies were performed by Brunel University. They were working with the human embryonic kidney cell, and this was due to the fact that kidney filters blood, so if there was some metal ion released in the blood, this should be able to find it. And the results were quite good. The cytotoxicity assessment showed that both the uncoated and the coated beta-type titanium alloy do not cause toxic effects and show good cell adhesion. So the purpose of this presentation was to communicate the innovation behind this project. Thank you for your attention.